Okay, welcome to the Chapter 1 and 2 review, and we're going to take a look at how we answer these so that we're in preparation for the Chapter 1 and 2 test. So let's start with number 1. It says, please identify the location on the blank periodic table of halogens, noble gases, and alkali metals. So one of the first things that we looked at on the periodic table was its layout. And here's a pretty good representation of where we can find all these identifiable groups. Let's remember that groups are the columns, and periods are, of course, the rows. So we're looking for groups that include noble gases, halogens, alkali metals. This periodic table is color-coded, and it tells us where we can find all of these right here. And so here we're saying that the alkali metals are this one, Group 1. We'll call Group 1. We'll say this is alkali. Let's spell that correctly. We'll say Group 1 is alkali metals. If we were trying to identify the noble gases, we find them over here in this red group. This is group 18. Remember that noble gases are all the elements that are non-reactive. So we'll say group 18, noble gases. And finally, the last one is asking for is the halogens. And according to this table, that's this group right next to the noble gases. And we remember that the noble gases, the halogens, are completely toxic. So anything chlorine, bromine, iodine, fluorine, they have a tendency to be toxic. Anything that breathes them or is exposed to them, it tends to be lethal. We'll say that group 17 is the halogens. Okay. So if we were going to identify these here, we would say Group 1, alkali metals. We would say Group 17 here is the halogens. And we would say Group 18 here is the noble gases. All right, number 1. Take a look at number 2. One of the things that we were trying to explore in the various labs we did, in particular Lab 1A, was we were exposing different materials to water and see if they floated. And let's remember that water has a density of 1 gram per cubic centimeter. What we noticed is that anything that has a density of less than 1 gram per cubic centimeter floats in water. Pretty good test, right? Our cork floated in our water, but anything that has a density that is greater than that, anything that has a density that is greater than 1 gram per cubic centimeter, we would say sinks in water. Our acrylic cube, our brass cube, all of those things would sink in water. So which of the following solids would float in water? We're looking for solids that have a density that is less than 1. That would include cork, butter, ice. Every other solid has a density that is greater than water, so of course they would not float. So the answer to this question would be cork would float in water. We know that butter would float in water, and we know that ice would float in water. This next question is asking, would ice float in gasoline? And the way we answer that one is by comparing the densities. We know that ice has a density of 0.92, but gasoline has a density of 0.67. So for something to float in something else, its density has to be less. But because ice has a density of 0.92 grams per cubic centimeter, that's density is greater than gasoline's, which is 0.67. We know that looking at our table, gasoline has a density of 0.67 grams per cubic centimeter. And so, of course, the answer would be no. You'll see a question like that on the test. It says number 3, find the density of a material given that a 5.03 gram sample occupies a volume of 3.24 milliliters. I'm going to go back to one of the labs and find a useful piece of information. Here we're looking at this particular piece of information from lab 1A, and it says that 1 milliliter is the equivalent of 1 gram per cubic centimeter. So what I'm going to do is I'm going to use my screen snip tool. I'm going to copy and paste that, and I'm going to bring it back to this review that we're working on. Let me get there. And we're going to plop that right here so that we can reference this. Make that smaller. Remember, oops, we don't want to do that. Remember that 1 milliliter is equal to 1 cubic centimeter. So it's not difficult to express our answer in grams per cubic centimeter because 1 milliliter and 1 cubic centimeter are the same thing. So it says express the density or find the density in grams per cubic centimeter. It gives us a mass. It says our mass is 5.03 grams. It gives us a volume of 3.24 milliliters, which is of course the same thing as cubic centimeters. So we're going to plug in our mass here. We'll say 5.03 grams. We have a volume of 3.24 milliliters, which is the same thing as cubic centimeters. And we'll take our calculator. Helps if we turn it on. And we'll say 5.03 divided by 3.24. And of course our units will be in grams per cubic centimeter, and this is telling us we have a density of 1.55 grams per cubic centimeter, because cubic centimeters and milliliters are the same thing. All right, let's get another piece of helpful information from another activity we did. This question is asking what is the mass of a sample of material that has a volume of 55.1 cubic centimeters and a density of 6.72 grams per cubic centimeter. Here is a useful tool. This is the device that we use to derive the equation that we want, and in this case it's asking us to find mass. So we're going to use this version. Mass is equal to density over volume, or density times volume. Mass is equal to density times volume. It gives us a volume of 55.1 cubic centimeters, and it gives us well, let's put this in the right order. I apologize. It gives us a density of 6.72 grams per cubic centimeter, and it gives us a volume of 55.1 cubic centimeters. So we're simply going to multiply these. Remember that when we do that, these units cancel, and that means it's going to leave our answer in grams. So we know our answer is going to be in grams. Let's take our calculator, and we'll say 6.72 times 55.1, and here is our mass, 370.272. Feel free to round that, 370.3 grams. Okay, here we go. Number 5, it says a sample of kerosene has a mass of 0.451 grams and is asking for the volume. Two things. We're going to use this guy to give us the volume because it tells us over here that volume is equal to mass over density. So we have a mass right here. Volume is equal to mass over density. Our mass is 0.451 grams. Where are we going to get the density to find the volume? And of course the density, we can find it right here. Kerosene has a density of 0.82 grams per cubic centimeter. So we're going to plug that right in here. 0.82 grams per cubic centimeter. Obviously, grams is going to cancel. It's going to leave our answer in cubic centimeters, which is what we want. So let's crank this out. We know our answer is going to be in cubic centimeters. Here's our calculator, and we'll say 0.451 divided by 0.82. We know our units cancel, and we get a volume of 0.55 cubic centimeters. 0.55 cubic centimeters. All right. Let's get to part 2. This is going to be our conversions section. So let's get another helpful piece of information here. So what I'm going to do is I'm going to drop this right here. This is our metric conversions chart. We're going to reference this quite a lot. And this first question is asking us, how many grams are in 882 micrograms? So let's set this up like we've been doing. How many grams is the equivalent of 882 micrograms? What I know from reading this conversion is that the relationship between micrograms and grams is that 1 microgram is the equivalent of 0.000001 grams. So when I set this up, what I'm going to ask is, okay, we're trying to go from micrograms to grams. We're going to put micrograms on the bottom. We're going to put grams on the top. 1 micro anything is 0.000001 of that thing. So all I have to do is multiply across the top and divide by the bottom. If you take your calculator, you can do it this way. We'll say 882. We're going to multiply this by 0.000001 and divide by the bottom, which is 1. And here's how many micrograms are in a gram. Uh-oh, is that scientific notation? Oh no, that looks like this. 8.82 times 10 to the negative 4. That, ladies and gentlemen, is a way of saying 0.000882 micrograms. That's all you do. You can leave it in scientific notation. You can write it like this. Up to you. Here's another one. How many milliliters are 0.603? Uh-oh, what's this big M? That's something called mega. You see that here. Mega is right there. And what this tells you is that 1 mega anything is 1 million of that thing. So we're not going to go directly from milliliters to megaliters. That tends to get a little weird. So here's how we're going to do this. We're going to set this up by asking how many milliliters are the equivalent of 0.603 megaliters. All right. Can't go directly from one to the other. But what we can do is go from megaliters to liters. How are we going to do that? According to our conversion, 1 mega anything is 1 million of that thing. So 1 megaliter is 1 million liters. So 1 megaliter is 1 million liters. If you want to write that in scientific notation, this chart tells you how to do that because, where did it go? In the scientific notation format, that's going to look like this, 10 to the 6, right here, 10 to the 6. So if you wanted to write this in scientific notation, if you didn't want to write all those zeros, you could simply write it as 1, let's get that red pen going here, 1 times 10 to the 6 liters, and that'd be the exact same thing. Now, because we want to go from liters to milliliters, we're going to use our conversion chart. And we know, if we look down here, 1 milli is equal to 0.001 of that thing. If we're going to write that in scientific notation, we could say 1 milliliter is equal to 0.001, or if we wanted, we could say 1 times 10 to the negative 3 liters. All we're going to do is multiply across the top, divide by the bottom, multiply across the top, divide by the bottom. So I'm going to take my calculator and I'm going to say 0.603 times 1 times 10 to the 6th. We're going to divide that by 1, which is not necessary. And then we're going to multiply that by 1, which is not necessary. And divide that by 1 times 10 to the negative 3rd. And our answer is 603 million milliliters. Our answer, 603 million milliliters, or 6 times 10 to the 8 milliliters.